I am Andrei Platzer, and my research develops the logical foundations of cyber-physical systems to characterize their fundamental principles and to show how we can design computers that are guaranteed to interact correctly with the physical world. The cyber-physical systems analysis problem can be explained with an aircraft example. If you are the pilot of this aircraft, or if you're designing the computer for this aircraft, or if your job is to understand whether that computer has been programmed correctly, then you will notice that your aircraft is dangerously close to two other aircraft. That will make you acutely interested in understanding which of those control decisions are safe for aircraft collision avoidance. But that late in the game, there is simply not enough time to sit down with a sheet of paper and draw careful trajectory plans to understand which of those to reject because there's a risk of collision and which ones are safe. If only there was a technology that could quickly tell the pilot how to get out of this situation again. Computers are blazing fast, but even computers still have to be sure that their chosen trajectory will indeed be safe always. And we need to make sure ahead of time that computer programs will always give safe advice, not just in this particular instance here. Many other systems have similar characteristics, for example, cars and robots. They're cyber-physical systems, or CPSs, that combine cyber capabilities with physical capabilities to solve problems that neither party could solve alone. The main concept behind the safety analysis of cyber-physical systems is differential dynamic logic, with which you can specify and verify CPS safety. Here's my favorite example, the Wally robot. The formula Wally box x not equal m says that all runs of the Wally robot are such that the positions x that Wally reaches is different than the obstacle positions in all the states that Wally can reach. Of course, we should be more precise about Wally's control and how he moves. So this formula says that Wally is always safe at the position x that first follows a discrete control where if a start braking condition is true for Wally's position in the obstacle's position, well, then Wally chooses an acceleration that is minus b, so a negative number. And otherwise imagine it, Wally might speed up, which isn't written down here. After this discrete control, Wally will follow a continuous differential equation where Wally's position is changing with a time derivative equaling the velocity, while the velocity is changing with a time derivative that equals acceleration. And the whole process repeats, so you will have a discrete control and a continuous dynamics, and then a discrete control and a continuous dynamics. And overall, the formula says that all of these runs are safe. Now this formula has a precise meaning, but the only trouble with it is that it isn't true in all states. Well, alright, but logic is good at managing assumptions. For example, you can say if Wally doesn't start in a collision state and his brakes work and some kind of other assumptions, then all behavior of the Wally model are such that Wally's position will never be the obstacle's position, so it's safe to turn Wally on. The best thing about differential dynamic logic is that you can not only use it to unambiguously state your favorite correctness properties for your CPS, but can also prove them correct in differential dynamic logic once and for all. This is where the axiomatization of differential dynamic logic comes in. These axioms here are equations of truth. For example, the highlighted axiom tells you that a system that has a choice between alpha or a beta is always safe if and only if, well, all the alpha choices are safe, and independently, all the beta choices are safe. By using this equivalence from left to right, you reduce your question about a system that has a choice between, let's say, accelerator brake, to one that only has acceleration choices and its safety analysis, and independently another that only has braking choices. And indeed, all the other programming languages' axioms are like this. They decompose program operators of differential Deming logic from left to right. One of the remaining questions is what to do with differential equations. Most are so complicated that they could hardly solve them. But when you want to know if a differential equation could ever enter these bad blue regions, then it is enough to check locally if the differential equation ever points from a safe state into the bad blue region, because following this direction would then be trouble. If it never does that, well, then intuitively we only ever go from a safe state into a safe state. This is the differential invariant principle, proving invariance for differential equations, regions we can never leave. Another logic principle generalized to differential equations are differential cuts. If you investigate a differential equation and show that it never enters this red region, then, well, you can cut it out of the state space because the system can never reach it. If you do that repeatedly, you will ultimately notice that the system ran out of bad blue regions and of course is safe. Another logic principle are differential ghosts. If you encounter a differential equation x prime equals f of x that you cannot understand, then differential ghosts let you introduce a new differential equation y prime equals g of xy, which, if you do that cleverly, enable you to read off new invariants relating the old state x to the new ghost state y, which indirectly helps you understand what x does from its relationship to the ghost y. These picture intuitions correspond to logical proof rules that capture sound reasoning principles for differential equations. With some twists and turns, they work together to prove all true invariants of differential equations and disprove all false ones. Differential invariants prove an invariant property P by proving its differential P prime. So think of it as deriving something somehow. The rule tells you precisely how to. Differential cuts allow you to prove a property C and then assume the property C, which is like a logical cut or a lemma in logic, except you do that in the middle of the differential equation dynamics. And differential ghosts rephrase an invariant P to the existence of a ghost Y for which G is true, and then argue that G itself is invariant with the additional differential equation y prime equals g of xy for the ghost. These principles of differential Deming logic do not just enjoy a sound and complete theory, but also have many useful applications in practice. For example, in safety technology for cars or even autonomous cars, pilot support systems or autopilots, as well as robots that move near people. All of these are areas with a lot of benefits, but only if you get them safe. This is a short overview of the logical foundations of cyberphysical systems. You can learn a lot more about it in my textbook. It provides you with strong analytic foundations, but also with roll-up-your-sleeves practical theory-improving advances, as well as significant applications, and provides an opportunity to bring many areas of science together. It covers a logic and a proof approach for cyberphysical systems with programming languages, theory-improving, and the key insight of multidynamical systems. Multidynamical systems are systems that are characterized by multiple facets of dynamical systems. They are exploited in the differential Deming logic as it keeps decomposing bigger systems into their simpler pieces, thereby simplifying the analysis.